So here is an example of fluorine. Each fluorine atom has 7 electrons in its outer shell, wants to get to 8, so it wants to share with another atom of some kind in order to get that. And so if another fluorine atom is there, each of them wants 1 electron, so it can form a bond between them. And in this bond, 1 electron is shared either way. So that effectively both fluorine atoms get that 8th electron, and they sort of merge their outer shells together to do that. Sometimes you'll see in chemistry, you will actually trace out the outer ring here and count the dots for electrons. It's a good way to keep track of things. We're going to go with a little bit simpler model. Oh, and here's showing that covalent bond. When this happens, these electrons are actually going around both atoms, filling up their shells. Okay. Here's how we are going to determine and build these molecules. It's a couple of the rules you already know. So first thing we're going to do is, for each atom involved, we're going to say how many valence electrons does each atom already have. So how many outer shell? That's the number across the top of the periodic table. You draw a dot around each atom for each valence electron, and then circle electrons in atoms that will be shared. So do this for each atom. So, I thought I had we're not going to do this method, so I'm just going to bust through it, and we'll use a different method. We'll do this until each one has a full shell, and then each time it shares it doesn't just give one up, it actually sort of gains one because they're sharing. So here is an example of how you would draw it out. So let's look at carbon bonding with fluorine. So how many valence electrons does a carbon have? 4. So how many bonds will it want to form? It'll want to form 4. Fluorine here has how many valence electrons? 7. So how many bonds will a fluorine want to share? Just 1. So the way that we would apply this, and we already got that. We've got carbon. It has 4 valence electrons. We'll want 4 bonds. We have fluorine with 7 valence electrons. It will want 1 bond. So then here's where the drawing part goes in. We draw the carbon, and around it 4 electrons to represent the 4 valence electrons. We get a fluorine and draw its 7 around, and electrons are paired in a way that we're not going to discuss, but that's why we draw them out. Typically, if there are pairs of them like this, we'll just draw them together. Now, carbon and fluorine can get close enough together to share 1 electron each. That's all fluorine wants. This counts as an electron for fluorine, which brings its total up to 8. It's not interested in sharing anymore. It's basically operating like one of the noble gases now that don't bond with other things. It's just not going to share any. They're too tightly held. But carbon, now it has 1, 2, 3, 4, 5. It still needs 3 more bonds in order to fill its outer shell. And so while it wouldn't bond to this fluorine, it could attract another and share an electron with it. Now it's up to 6. Get another one, share there, and so it actually ends up attracting 4 fluorines. Each fluorine only wants to bond once, but that gives carbon 4 bonds. Makes sense? Carbon dioxide, we'll give you another example before we go on. We have carbon and oxygen, so carbon, just like our last time, 4 valence electrons, it'll form 4 bonds. What about oxygen? How many valence electrons does oxygen have? 6. How many bonds will it form? 2. Okay, so we'll draw our carbon and the electrons around it. We'll draw oxygen and 6 electrons around it. Now, this oxygen is perfectly willing to share more than once because it needs 2 in order to fill its outer shell. It could share with the same thing, or it could share with 2 different atoms. But carbon here says, well, I'm still willing to share. So this would be 2 bonds in between. carbon is not, oxygen's full, but carbon isn't, so it would attract another one and share a pair of electrons with it, giving you the total here with it, which is carbon dioxide. 1 carbon, 2 oxygens. And I don't know if I've got my next. Okay, so now drawing them, we're not going to draw this out every time. There's a much more straightforward and simpler way, something called bond lines that we're going to practice. This is a really good tool for helping you draw out on paper how many of each are going to go. We're going to use Legos instead, though, to help us. So you'll see this again in chemistry in a couple years, rather than the Legos. It's a more established method to do it. But now drawing them, instead of all the dots, we're going to start with symbols and draw this one you should get down. Draw a line between any 2 atoms that share an electron pair. We call this a bond. If it shares more than 1 electron, we'll draw multiple lines, and I'll give you some examples for this. So here's our carbon tetrafluoride. Oop, and I will write it out. So we saw 1 carbon, and it shared 1 electron with each fluorine. So if I have my first fluorine here, the way I show that it's sharing 1 electron either way is to draw a single line. I don't really connect one letter to the next, but a line in between. This tetra, of course, means 4. There are 4 fluorines around. Each one is sharing a bond with carbon. So we have a bond to this fluorine, a bond to a 3rd fluorine, and a bond to a 4th fluorine. This shows 1 carbon, tetra, 4 fluorines. One thing that I have seen a lot in the past, which we cannot do, is to say, oh, I've got carbon, I've got fluorine, I know they're bonded 4 times. Why can't we do this? Yeah, of course.
Because it looks like it's connected to like 4 electrons.
4 electrons, but only to 1 fluorine. So we can't do exactly right. Fluorine can only ever form 1 bond, so we have to have the 4 fluorine atoms represented. I'll give you a moment to catch up before we do the second one. Our second example that we saw was carbon dioxide. We're going to, again, draw it in the same sort of orientation. We have a carbon, we had an oxygen over here, and this was sharing 2 pairs of electrons. So we draw 2 lines. This is called a double bond. It shows that the carbon and oxygen are sharing 2 pairs of electrons between them. And if we count up the number of valence electrons an atom starts with and the number of bond lines, that tells that we want that to be 8, except for hydrogen. So oxygen starts with 6, like we said, and it's got 1, 2 bonds, so it's up to 8. Carbon, though, has 4, and then 1, 2 bonds, so it's only at 6, and that's why we know it needs another oxygen on the other side. So this sort of drawing them this way takes a place of drawing out each of the individual dots, although those individual dots can really help you focus how you're going to do it. Unless you have Legos. In our Lego lab, which it looks like we will have to wait until tomorrow to get, I have 4 different sizes of Lego to represent the number of bonds. Each Lego has a certain number of these buttons on top, the way that it connects with other Legos, and that each of those buttons represents a bond. So for example, this just has a single button on it. Which atoms would this represent that only need a single bond? Fluorine. What else? Chlorine. Bromine. Iodine. Astatine. Yep. And since that's a lab created one, those don't actually have electrons going around them. Usually it's just the nucleus, so we will not use that. Astatine we could. And what other element needs a single bond?
Even hydrogen.
Hydrogen does. So this could represent any of those atoms in a molecule. This one has 2 buttons. What atoms could it be? Oxygen, sulfur, selenium, tellurium. Yep.
Polonium.
Polonium is actually now it's back on the metal side, so it's actually going to behave pretty differently. And even tellurium is a transition one, so sometimes it behaves this way, sometimes other. Okay, 3 buttons. Nitrogen, phosphorus, arsenic. Yep.
Antimony.
4 buttons. Carbon and silicon. Yep.
And
Maybe
germanium.
germanium if it bonds covalently. Yep.
Could be tin too.
Okay, so now we'll go over this again, but just for our viewing audience. There are some rules that you will have to follow in order to use this as a modeling tool. So let's take our example of carbon dioxide here to go for. So carbon needs 4 bonds, and we have 1 carbon in this molecule. So we're going to want 1 brick that has 4 bonds on it. We have 2 oxygens, and oxygen is an atom, like we said, that needs 2 bonds. So we're going to take 2 of the double button pieces. So we have 3 in total, a carbon and 2 oxygens. In order to put these together now, you have to make a wall that is exactly 2 bricks high all the way across. So you can't leave something hanging over the edge like this. That's no fair because that's an unbonded electron. And you can't have them separate. So you couldn't put these 2 together and have these separate. They all have to make 1 block, 1 wall. So this one is not too bad. If we put the 2 oxygens either on the top or bottom, doesn't matter. That illustrates what we've got here. This oxygen is sharing 2 buttons with the carbon. So the oxygen has 2 bonds to the carbon. The other oxygen also has 2 buttons connecting it to the same carbon, which represents this. We're going to practice tomorrow not only how to figure out how to put these together following those rules, but then how to draw them out to make our bond line structures. But we'll start that first thing tomorrow, maybe after a very brief review.